Hello everyone. Our video presentation is going to be over the comparison of dimensional analysis and modeling of traditional versus hypersonic aircraft. So here's just a quick overview of our outline for this video. So firstly, what is dimensional analysis? Essentially, it consists of fluid mechanic problems where several experiments are required. To put the amount of experiments required into perspective, in order for NASA to first create the prototype of the Chance Vault FAU, they first created 386 models to test whether the prototype will function properly. So you can imagine the amount of materials and funds NASA would need if they decided to run their experiments on prototypes rather than on smaller models. In situations like these, dimensional analysis is extremely powerful because it allows us to scale up the results done on these models to the prototypes, meaning that NASA was able to avoid having to create and test hundreds of expensive prototypes, which allowed them to improve upon this prototype so much so that it was even used in the Vietnam War, and it was known as the Vault FA Crusader. So speaking about the Vault FA Crusader, which was the direct product of NASA's 3 years of experimentation, it turned out to be crucial in various historical events such as the Cuban Missile Crisis. It also performed excellent throughout the Vietnam War. And the reasoning why I mentioned this is just to show just how impactful dimensional analysis is, considering that this one tool led to the creation of a war aircraft that helped the United States for many decades. Imagine that, one simple tool being the variable that tips the scale in a worldwide power struggle. So then, how exactly is dimensional analysis performed? Well, in a pipe system, we consider a steady flow of an incompressible Newtonian fluid that flows through a long, smooth wall horizontal circular pipe. In doing so, by listing all the variables involved in this typical fluid mechanic problem, we are able to create the dimensional parameters. And we do this by using a theorem created back in the early 20th century, known as the Buckingham pi theorem. This theorem provides a method for computing sets of dimensional parameters from the given variables, even if the form of the equation is still unknown. So by following the steps seen to the right, they are able to basically find the recipe in creating various relationships among the pi terms, such as the Reynolds number and friction factor, which are both essential formulas in many fluid mechanic problems. So now moving back to how this tool is used on aircraft traveling at traditional speeds, this is done by using a CFD tool, also known as computational fluid dynamics. So for example, in current industrial practice, the Reynolds average Navier strokes, or RANS equation, is used. By looking to the chart in the middle, we can see that the RANS is the most accurate due to its complexity, but because of this, the RANS is also the most expensive as well. Although speeds that are above traditional speeds require an even more complex computational tool, and because of this, it will also be even more expensive. So in this slide, we can see an animation of the exterior of the plane experiencing Mach 2.2, which is still under the category of traditional speeds. Those white lines that appear at the tip of the plane along with several other areas are shock waves, and we're going to see later in speeds above traditional speeds that these white lines, rather than pointing outwards of the exterior of the plane, we'll actually see them along the exterior of the plane as if it were sticking onto it.
So hypersonic flight is defined as anything more than 5 times the speed of sound. This means that a hypersonic jet has the capability of traveling around the world in under 8 hours, compared to 32 hours for traditional aircraft. At these speeds, we start to experience entirely different physical and fluid phenomena, which means we need more complex equations. So that leads me to the dimensional analysis and modeling. In order to do dimensional analysis and modeling of aircraft, you have to utilize every resource available, due to the fact that you have to account for incredibly high temperatures from friction and shock waves, ionization and chemical changes to the fluid flow around the aircraft, and in addition, CP and CV are no longer constant at these speeds. This leads to incredibly complex and complicated equations that need to be solved, requiring things like supercomputers. In addition, modeling of hypersonic aircraft is a necessity because these speeds are incredibly expensive and incredibly dangerous, which means that having a full-scale prototype is not safe at all. Now moving on, you can see the image on the right here that shows the different models that you might see. The very first one is traditional speeds where you only experience flow separation. The second is the development of shock waves during Mach 1. And then the last one is where we see shock waves starting to stick closer to the surface and intense heating and friction that you would experience in hypersonic speeds. The next image kind of shows an example of computational fluid dynamics of hypersonic flight. This is NASA's X-35 spaceplane. You can see at the very bottom of the aircraft where the air intake is for the air-breathing engine is where the most friction is experienced. That's because the plane is designed kind of like a wedge, so there's very little surface area to experience the friction, therefore reducing the temperatures on the aircraft. So looking for direct comparisons between the two, we see that in traditional aircraft, the Mach and Reynolds number, or things like the Reynolds average Navier-Stokes equation, are more than enough to allow characterization of the flows that you experience. In contrast, hypersonic flows need additional categorization like I mentioned earlier. Some of the things we have to account for are total energy, total enthalpy, total pressure, stagnation temperature, and flow velocity. These increased parameters make analysis and modeling incredibly complex and requires the utilization of a supercomputer in order to complete the analysis. So looking for future outcomes of hypersonic flight to become more viable, we're going to need more complex computational simulation. Currently, there's no standard for doing a modeling and analysis of hypersonic flight due to the increased parameters that we experience. The image on the right shows the re-entry of a NASA capsule coming back into Earth from the space. And you can see that the temperatures on the bow as they re-enter are upwards of 12,200 Kelvin. These kind of temperatures are more than enough to melt steel and are incredibly unsafe for human life. This means that the materials that we have when we design these aircraft need to have higher temperature resistance and hot hardness in order to overcome these hurdles. In addition, air-breathing engines that are used in hypersonic flight need to become more efficient to overcome the drag forces required for hypersonic plane design. With that being said, hypersonic flight clearly has a lot of potential to change the world. However, there's many significant hurdles that need to be overcome before it can become more commonplace. I hope you enjoyed our video, and I hope that you learned a little bit more about modeling and analysis of hypersonic speeds. Thank you.